Looks like we're live. Hello everyone and welcome to yet another recreational programming session with Azuzin. Let's make a little bit, just a tiny bit of an announcement as usual, and yeah, and see how it goes. Come on, Discord, you can do that. I believe in you, Discord. Red Circle live on Twitch. And what are we doing today on Twitch a television website? Today we're doing Google in C, aka Coogle, right? So that's what we're doing today. Twitch.tv/Tsoding, and I'm gonna ping everyone who's interested in being pinged. There we go, the stream has officially started, the stream has officially farted. So hello everyone, welcome. So yeah, yesterday was an interesting stream. Yesterday we were exploring the possibility of implementing something like Coogle for C. Do you guys remember what is Coogle? Right? Do you guys remember what is Coogle? So we have the Coogle here in the chat. I wonder if we have it in the description. Yeah, we do have it in the description. So let's actually open Coogle and just like see what the hell is that? What the hell is that stuff? So essentially Coogle is a pretty cool thing for Haskell specifically, right? So you can just put some sort of a signature in there, and it will try to match a function with a similar signature. For instance, I want to be able to take a string and turn it into an integer. Can we find, yeah, there we go. So UTF-8 encoded length accepts a string and returns an integer. Right, so you search in a function by its meaning, by its intent, not by its name. The name is kind of irrelevant. What's important is the signature, right? So you know what kind of arguments it accepts, you know what kind of stuff it returns, and stuff like that. So that's actually very useful. For instance, if there's something that accepts a string and returns a string, right, it's nothing particularly useful, right? So maybe a character accepts a character and returns a character, something like, yeah, to upper. For instance, you can take a character and bring it to uppercase or to lowercase, like however you want. Right, so essentially you may need some sort of a function. You can think about a possible signature of that function, and you can put it in there, and it will kind of roughly tries to match and find function that maybe suits for you. So it searches in the standard library. As far as I know, it also searches sometimes in third-party dependencies somewhere, so it's actually kind of cool thing. And it's so cool, I couldn't see that like a similar thing being implemented in other languages, even functional ones, right? Even functional programming languages kind of fail to replicate this kind of awesome functionality. I don't really know why. I think it's relatively easy to implement. And what I want to do is essentially implement this entire thing for C. That's right. Because quite often, I just like look for an appropriate function somewhere in Raylib, and I struggle to find anything, right? So quite often I just like want to do the Coogle style search by types, but I can't do that. To be able to do that, we need to actually be able to parse C. Luckily, on the previous episode, on the previous stream, we learned how to parse C. So the solution we came up with, we used Clang with Jai. And usually I don't like to use the Jai on my streams because it kind of makes it difficult to share the source code, because not everyone has an access to Jai. But the reason I used it is because it already had libclang in a standard library. Well, I mean, it kind of like got there accidentally. Imagine the language being so Chad, it has libclang in a standard freaking library. Can your Rust do that? I don't fucking think so. These, okay, I'm gonna fucking show you, seriously. Like, look at the standard library of Jai. Look at the standard library. So you have a bindings generator, and the bindings generator contains libclang. Like, libclang comes, just like Billy Harrington, with the Jai distribution. Right. So the other shit you can have, you have curl. Jai comes with curl, direct 3D. It comes with like gamepad support, free type support. It comes with OpenGL support. It comes with IMGUI support. Like it's all there, right? Can your Rust do that? I don't fucking think so. I don't fucking think so. All right. So, and yeah, so that's why we use it, because it has the clang already available. And we create a very simple example, which takes the raylib header, right? So this is a huge raylib header. Well, it's not that big, but it's 1,000 and almost 600 lines of C code. And essentially, we implemented a parser of this thing. So essentially what it does, it just like traverses through all of the function definitions and parses its signature. So as you can see, we parse the types of the arguments and we parse the type of the return, basically return type, right? So, and like I also print the location, which is kind of compatible with Emacs. So I can run it in Emacs compilation mode, and I should be able to actually jump between the definitions and stuff like that. So let me quickly do that. I want to see that, right? Yeah, essentially I can just like jump between these things. I can pick a particular function and just jump between all of that stuff. All right. So essentially the only thing that is left for us is to collect all of this information in some sort of like a centralized database, like in memory database. We're not going to use the real database. Like I just like use a data structure. I just use the database as the synonym for data structure, right? So just put that in some sort of like a dynamic array data structure and just like query it. So one of the things we'll have to come up with is probably some sort of like a query language, a very simple query language, so that we can describe the signature of the function we're trying to match, and essentially come up with a way to match that signature with the signature of the function in sort of like a fuzzy way, if you know what I mean, right? Because we don't want to match them strictly, because it's not going to be particularly useful. The thing about Coogle is that like it can, well, I mean, in this specific case, it matches only character to character, but you can just supply a function that accepts A and returns B. And it will match all sorts of things, right? It will match like a lot of different things that like accept A and return B, like V, P, and stuff like that. So it matches things like sort of fuzzily, right? So we need to come up with a sort of like a language to describe the signatures, and also a way to match those signatures somehow fuzzily. So I think that's going to be interesting. So we've got some subs. We've got an anonymous gifting sub to Black Dick in Your Butt. Thank you so much for gifting the sub. Really, really appreciate that. So, how are you guys doing? Does it sound interesting? It sounds cool. So, since Jai supports WASM-ish from last template, would it be possible to add a web frontend for this? Can even make it look like Google? I mean, we don't really even have to compile maybe Jai to WASM. We can just basically use Jai to parse, you know, the data and put it in JSON format and just like implement everything in JavaScript. In fact, we don't even have to use Jai for this specific project, right? So there's literally nothing special about Jai. It's just like it already had a libclang set up. I can use C. C is way easier to compile to WASM than Jai. So, how can we do all of that? How can we do all of that? So, first of all, we probably need to collect all of the function signatures in some sort of like a dynamic array, if that makes any sense, right? In some sort of dynamic array, because right now what we're doing, we're just like iterating through them. So, right, I did a little bit of like a cleaning up of this code before the stream, right? So, and essentially what we do, we use the clang function clang visit children, and we're just like visiting the entire tree that we just parse, right? So there's a very cool function in here, right? So it accepts the cursor. And essentially, if I understand correctly how clang works, is that it has the notion of cursors, right? And cursor points at some sort of a node in AST. And with that cursor, you can traverse like up and down and stuff like that. And there is some visitors that accept cursors and can do recursion for you, because as a computer scientist, you're not supposed to know how to do recursion yourself, right? Because obviously, like a library for making languages should be user-friendly. Obviously, a person who is going to use libclang knows nothing about computer science and recursions. Obviously, we need to help them. We need to make like a recursive traversal for them, right? So I don't fucking know why, but I mean, maybe it makes things a little bit easier. But So quite often what I found, it is easier to just like have this helper function that I stole from the bindings generator that just takes all of the children from the cursor, right? So it uses this like child traverser and just collects them into an array, and it's just like easier to deal with this kind of thing. Right, it's just like easier to deal with this kind of thing. So yes. So maybe we need to define some sort of a structure, right? So that keeps track of the name of the function, the location of the function, and the signature of the function, right? So something like that. So let's go ahead and do that. So maybe we need to create a function, and this is going to be a struct. So obviously we need to have a name for the function, right? So this is the name, and or as the client likes to call it, it likes to call the name spelling. Though I think I do understand why they call it spelling, right? It's kind of really interesting. For instance, if you ask for a spelling of a type, it will return you this sequence of characters, right? So this is a spelling of the type string in C. So as you can see, it's not really a name of the type, it's the spelling of it. So it's the string that represents how it looks like. I think that's the reason why they call it spelling, right? So in the case of the functions, spelling means the function name. In case of the type, it means like how the type is actually spelled. So it is rather interesting. So maybe like when I encountered that name, I was a little bit shocked. It was kind of weird, but maybe it makes sense, right? For types, calling it spelling does kind of make sense, because this is not really the name of the type. The name is more like a char, but it's a constant char, and it's a pointer to the constant char. So it's just like, yeah, this is the spelling of the type rather than its name, because name, it's not particularly obvious in here. You know what I mean? You know what I mean? Right, I do understand why they decided to actually call it like that. So we got some subs. Thank you so much, Nazariel X, for a tier 1 subscription with the message. This reminds me a little the OpenGL doc indexer in Rust you wrote. Maybe not really. It is not aware of the type signatures and stuff like that. I mean, the only common things between them is that they search things. That's it. So it's very, the way they search things is actually kind of different, I think. I do believe so, right? So I wouldn't say that they're the same thing. It's just both of them are searches, right? So they just search differently. Hagveld, thank you so much for Twitch Prime. All right. So, all right. So we need to have the name of the function. So here is going to be the name, and we need to keep track of the arguments, right? So let's actually do args, and let's say that is going to be maybe an array, right? So do I want to make it a dynamic array? A dynamic array means that I'll be able to in the future like expand it, but maybe once I created this sort of like a function database, I'm not supposed to be able to expand it. So I think it makes sense to just keep it as it is. And we also need to have a return type, so I cannot use a return, so maybe I have to call ret. But we may have a return missing. We may have a return missing because it's void and stuff like that. So how do I indicate that it is missing? Right, it would be easier to maybe just like take it by a pointer, but that means I'll have to like allocate the whole structure thingy in the in a dynamic memory or something like that. Or we can just always have a string, and if we don't encounter the return type while parsing this entire thing, we always going to assign this entire thing to void. By the way, as far as I know, this is like a valid thing to do in here, right? So in Java you can have like default values, and this is how you define them, I think. And by the way, I suppose you have to do it like that, right? So you have to use a single colon in here, right? You're supposed to use a single colon in here. Okay, so we got some functions. Let's try to compile this entire thing and just like see agile linux main.jai. Right, main.jai, what do we have in here? We have a function and we have a redeclaration, of course. You can't just call your structure a function because it's probably already taken. It is probably already taken. Why I was being so careless? So how should we call that? Let's call it Coogle func. Right, so Coogle func. Right, so that should be fun. Function, freaking. Yes. Thank you. Function 2. Function 2. Why didn't I think about that? Like, I almost called it like a very unreadable, unmaintainable name. Now, this is the pinnacle of maintainability. Yes, function 2. And it's going to be called like that forever. That's right. Function 2. And if that pisses somebody off somewhere in the internet, you can't do anything about that. It's going to be called function 2 forever. Eat that. Maybe it's already taken to, yeah, okay, so we need to actually check if it compiles. All right, it's not taken. Perfect. It's not taken, right? That's actually very cool. Anyway, so here is an interesting thing. We need to somehow collect the functions, right? So we need to have like a global array of functions. So functions, and this is going to be like a dynamic array of function 2, right? So we want to have something like this. We can keep this a dynamic array, right? We can keep it a dynamic array. But it's kind of like not particularly pleasant. I would like to be able to pass the function as the client data to this function that is passed to the visitor, right? So as you can see, we're passing it to the visitor. So we provide the cursor to the visit children and the function with which you want to visit things, and this function traverses recursively for us automatically. And if you want to pass some additional information, you have to provide it as a third argument in here, and the visit children is going to provide that client data in here. What we're providing there is the GI context. We're providing the GI context, and GI context is a very interesting thing. It's a global structure. It's a global structure that has like things that you always want to use. Like it contains an allocator, a logger, something else. I don't remember. Maybe we can find a how-to in GI that explains how the context works, because it's kind of difficult to explain like right away. Okay, so context. So there's like a huge story. We can try to read this entire thing. Traditionally, in languages like C++, programs run into trouble when they want to control the way memory is allocated, while also using code written by someone else. In C++ specifically, the things you have to do to replace the allocator globally are ugly, error-prone, and add a great deal of friction with regard to linking, and they still may not get the flexibility you want. Right, so for example, you may want one module to allocate its memory for one particular heap, another module to allocate from a different heap, and so forth. Memory allocation is not the only kind of operation where you may want this flexibility. Logging and assertion handling are other such cases. You might want logging from one module or from one subtree of the program's call graph to go to one place, and logging from another subtree to go to another place. Right, and this is basically where the context comes in. So the context is like this thing that is always available, right? And it contains the logger and allocator and stuff like that, and you can replace the allocator. And essentially you can write a third-party library that just uses the standard allocator, and then the user program that uses that library can swap out that allocator very easily, and the library should not be concerned with that, right? So, which is kind of cool. But that raises the question, like, does it mean that the language creators can predefine what goes into the context, right? What if I want to extend it? Like, what if I discover another thing that is neither logger, not allocator, nor something else that also needs to be shared through the context? How do I add things to the context? Right, and there is a special sort of like a directive, right? So it's literally called add context, right? So if you think about the context as a structure, you can add fields to that structure at compile time, right? So, and like different parts of the program can add different things to that context, and all of that is compile time. So at compile time, you say, okay, extend context with this kind of thing. And essentially what we can say is that, all right, so let's actually add this entire thing to the context. So now our context, right, that we actually provide as the user data for this traverser now has fields function, right? So here we may refer to the context, and now it should have functions. Right, so we can just add fields in there. We can just add fields in here. So this is basically what we need to do, right? So essentially I already passed the context as the client data, but I also need to pass functions in there. So you can add functions to the context if you want to, right? Something like that. And this is probably where we want to start collecting the functions and stuff like that. So yeah, essentially here we have the name of the function, right? So here we have the name of the function. And we can maybe just create it. So here is the func, and I'm gonna say that this is a function too, right? And we got the name, and we get the name through the clang. It returns the string, right? So this is the clang string that you should dispose at the end of the scope. But then to get it as a string, you have to first get its C string representation, and then convert that C string representation to the GI representation, and only then you'll be able to assign it as a name. Right, which is a pain in the ass a little bit, but I guess that's fine. Right, but furthermore, this string is going to be disposed, so we cannot just like assign it like that because it's going to be invalid. Right, we need to copy the string, right? We need to do something like copy string. So it gets preserved and stuff like that. In fact, in a bindings generator, I think I saw, like right before the stream, a very cool function. So they also encounter this kind of problem, right? So that you have to take the strings out of clang all the time and keep disposing them, but sometimes you need to copy them because you want to use them later, right? They also encountered that problem. And they come up with a funny function. I think it's called copy and... yeah, copy and dispose. It's so fucking funny. Right. So it accepts the clang string, then it just gets it, converts it to stuff, like copies it, and instantly disposes it. So the GI string is the only thing that you're supposed to use afterwards. Right. So that's basically how it's supposed to work. Dispose, you mean you. Listen, I didn't come up with that API. Don't blame me on the naming, okay? You mean. It's them who came up with this terminology, not me, okay? They call it dispose. I think they mean free. Right. They also call the name of the function spelling. And they call deallocating or freeing memory disposing it. It's not me who came up with this shit, okay? I'm suffering not less than you, right? It is what it is, and it isn't what it isn't. So what we're gonna do, I think I'm gonna use this particular style of doing things. I really like it, right? So copy and dispose. Right, sometimes, actually not sometimes, but majority of the time, the code that you have to work with is not yours. And there will be nobody to blame for that. And you will need to get shit done. So, it is what it is, and it isn't what it isn't. Is it not? I think it is. The missile knows where it is because it knows where it isn't. We got some subs, just a second. Thank you so much, John DiResta, for Twitch Prime with the message, I love it when you zoom in the chat. That's right. So I zoom into the chat so that I have a proof that I'm not talking to myself and not a complete schizophrenic. Right? So when I upload it to YouTube, right, I have a proof to the YouTube people. Look, this is not voices in my head. Look, these are real messages. These are the real messages. I'm talking to real people, I swear. I'm not that crazy. So, right, so it's very important. That's why I started to actually zoom in every time I answer the question or message in the chat. So that's very important. Alrighty. So copy in dispose. And I suppose the way we can do that is actually copy and dispose, and we can instantly assign this entire thing to name. That is actually very cool, right? So we get the spelling, we copy and dispose, and then if we want to refer to the name string somewhere here, we can just refer directly to the function name anyway. We need to keep track of the position of this stuff, I think. Chat. I think we need to keep track of the position of this stuff. So let's say that we want to have file name, right, which is going to be a string, and then line, row and column, right? So we need to keep track of the row and column. So this is going to be like this. Look at these disgusting columns. Look at these disgusting columns. Just a second. Oh, look at that perfectly aligned code. This is so fucking perfect. Oh my god. Anyway, can your Vim do that easily? I don't freaking think so. You need some sort of a third-party dependency. This kind of shit comes with the Emacs out of box. Aha. Okay, so what do we need in here? I wonder, every time I get the file allocation, do I have to dispose it? I don't think so, because I'm allocating the file on the stack, so that should be fine. So here, what I can do, essentially, I can get rid of the line and column, right? And I can just use directly function line and function column, right? And then, when I'm about to get the file name, I can do function file name. Did I actually call it file name? Yeah, I did call it file name. Get file name, and this is a string, so I can copy and dispose that bitch. I can straight up do that. That is very cool. That is very cool. So we already have line, column, offset. I have no idea what the fuck is offset, but maybe I can keep track of the offset anyway, right? So just in case, just let's keep track of it. God, it's unaligned again. But no worries, I'm gonna align it again. Oh, it's perfect. Perfect. Oof. Love it so much. Anyway, so alright, so that seems to be cool. So here we take the file path. We don't really have to do that. We can take that stuff directly. So this is the file name. This one comes from the line, column. It's actually not file, it's a func. It's a func. Okay, so that looks cool. And in here, right, so essentially what we do in here, right, we're getting the children of the function definition, right, we're not forgetting to dispose it afterwards, right, we're iterating each individual children, and we're looking at the kinds of the children. If it's a parameter declaration, we get the type spelling, right, so that gives us the type, and if it's a type reference, it's probably a return thingy. Right, it's probably return thingy, and we can directly actually do all of that. But before we start parsing this stuff, maybe I'm gonna just go ahead and add the function to the functions in the context. Can you do array add context functions, and I'm gonna just literally add func, right? So let's go ahead and try to compile this entire thing. It does not compile. Let's find out why. Because it doesn't have a name. This looks like you're trying to declare a variable. Oh yeah, thank you so much. Thank you. So we're not. Yeah, I keep using this Pascal stuff, Pascal style declaration and whatnot. Line is not because it's called row, right? I usually call it row. What else do we have in here? It is row. What else? And it's just a single name. And there we go, everything seems to be compiles. Everything seems to be compiling. That is actually perfect. If I try to now do the following thing. So we're iterating through all of the functions, and we can say something like this. We can put a line, so we separate everything from the garbage above, and we can say something like parsed, indexed. That's a fancy name I want to use in here. Indexed functions, right? And we're going to do context functions count, right? So after like indexing all of them, we can print how many functions we managed to index. Right, so let's just do that, and this is gonna be main, and did I add the functions there? What the fuck? Bruv. Why they're not... What the fuck is going on, mate? What the fuck is I think I know. I think I know, because we're not passing it. Do we have to dereference the context? Right, so because here we get the pointer to the context, but then we dereferencing it, so we kind of pushing the context, but the copy of the context. Is it possible to say, okay, can I just put a pointer in here without dereferencing it? Like, I don't really know how the push context, you know, thingy works. I don't really know how it works. It doesn't really work like that. Okay, so the context doesn't work the way I think it works, so yikes. One of the way we can actually, you know, fix that is just by literally doing that, just going back to the drawing board and just like, you know, using the global stuff, right? And in here, of course, we're going to refer to it globally, and in that case, it works, right? So I think I do not understand how the context works. You copy in the context so the array is modified. Yeah, I figured. Right. So, but how do I say that I want to push the context, but also I want to modify the previous? I don't think there is a way to do that easily. I don't think so. Right. I don't think there is a way to do that, unfortunately. Unless we make this thing a pointer. And then add context, but that means I'll have to allocate it somewhere in dynamic memory or something like that. I don't know. So all of that makes me think that it's easier to just keep it as a global variable. You know what I mean? So it's just like easier to use it as a global variable. Look at that! Look at that! We have a structure function 2, and it's used in a global variable. How many people this can piss off, I wonder. How many people this can piss off? Global variables, function 2. Oh. Billions upon millions of people will be pissed off. Anyways, I'm sorry. So now, I'll go back to that a little bit later and see if it's possible to just add it to the context, but I mean, it's not really that important, right? So I didn't think so. What's important is that we managed to index 517 functions, which is actually kind of impressive. It is in fact kind of impressive. So let me see what next we need to do. So if we encounter type ref, this is a return type. And we probably need to do the following thing. We're going to take the func, so this is going to be return, and we're going to assign it to, yeah, type spelling, right? But we have to copy and dispose. Copy and dispose. We don't have to do that stuff anymore, and I think we don't have to do that stuff anymore, so that's totally fine. Parameter declaration, it's basically the parameter, right? We can do a similar thing. We can do copy and dispose, but on top of that, we need to add it to the arguments, right? So let's actually do array add func args, and we're gonna just like literally add all that stuff in here. So that should be it, essentially, right? We can maybe get rid of these things, of the curly braces and stuff like that. So that's essentially what we're doing if we encounter any of these things. So we can maybe even do something like case assert false, because when I'm taking the children of a function declaration, this is the only kind of nodes I expect, only parent declaration or type ref, which is basically return type. So that's the only thing I expect. If I encounter something else, I think it makes sense to maybe print that, right? So we can say unexpected, you know, child kind, and we can print that kind, it kind. There we go. So that should be rather cool. I really like the default basically variables in here. It's so easy to just iterate arrays, like for array, and then you just refer to the elements of the array with it. Right, it just makes it very like compact in a sense. It's actually rather cool. So, okay, good. So let's now try to run it again. So if I go to semicolon, that's fine. That is totally fine. Procedure cannot find any possible overloads. Oh, okay. So this is what I was talking about. I wasn't sure if I want to modify the args in place. Looks like I do. Right. So let's actually make it a dynamic array. Right. Let's make it a dynamic array. There we go. So we basically got everything in here. So we're still printing those types. We're still printing those types. Let me quickly go and not print them. Where do we print them? So here's the function declaration, and this is where we print them. Okay, so here we don't really print anything anymore. We're just collecting all of the functions. As soon as we get them, we have them in here. We essentially have them here. In fact, we can just go ahead and print the functions. For functions, let's just like literally print them and see what kind of functions we've got, like so. All right, that's a lot of them. So I forgot to print the new line in here. Just a second. So let's just try to do that one more time. There we go. So a single function, we can just like find a single interesting function that maybe contains some parameters, like for example, get shader location attribute. So let's actually copy paste it in here. And this is how it looks like. So here is name. Here is the file where it is located. Here is the row where it's located. Here is the column. Here is offset. I feel like offset is not really needed, but anyway, the arguments that it accepts is shader and string. And what it returns the void. In fact, we can try to find it. So I'm going to go to ArrayLib to 1019. And in fact, okay, so we've got a mistake, right? So it returns integer, but it accepts shader and this string. So I got the return types wrong. Which is rather interesting. So I'll have to do something about that, but essentially that should be enough for us to actually search things, except we just need to fix this particular thing. So I'm thinking how we can fix all of that. How can we fix all of that? Maybe, just maybe, we need to go back to rendering everything. So I want to somehow break on this particular, on parsing this thing and look at all of the childrens that we get. I wonder how we can do all of that. Maybe we can create something like test.h, and literally copy paste that single function there. Right, I wonder if that's a viable thing to do. So we can go 1019, right? And I'm gonna just go and copy paste this thing in here and just hope for the best, right? Just try to parse specifically this, right? So here we are parsing that. I'm gonna try specifically test.h. I feel like it may not succeed because there will be, there is no such thing as RL API and shader. We can try to go ahead and define them. Define RL API. We can literally define it somehow like this, right? Doesn't matter. What else do we need? A non-type shader. Okay, so where is the shader? And that's literally it. So it's not that difficult of a definition. So it is super easy to just define it like that. So that should be fine. There we go. And yeah, we don't have a return in here, so that's actually perfect. That is actually perfect. I like that. So that means now in here we take all of the children, and I can just maybe print all of the children, right? So we'll just print each individual child it. So did I forget to put a new line? No, I didn't. Surprisingly, yeah, surprisingly we don't get a return type. So there is a really weird behavior, is that you only get return type as a child if you are returning a type def, right? If I do a type def, as you can see, you get this thing as the first one, which is really weird, right? Which is really weird. So, but if you refer to it as the normal thing, you don't get this as a return type, which kind of hints that you're supposed to get the type spelling of the return time somehow differently, and maybe that's the clue, actually. Maybe that's the clue. So there is a function get type spelling, and maybe that's what we have to use on the function, on the function declaration cursor, right? On the function declaration cursor. So let me give it a try. So literally, as we get the function declaration, I'm gonna do print. I'm gonna just put a frame in here, like I'm putting a frame in here, and I'm gonna just print that thing. So function decal type spelling, and this is gonna be like this. I swear to God, man, like clang, right? How do you even use clang? I have no idea. So what does it say? It. All right. So this has to be cursor. This has to be cursor, and yeah, it gives the entire signature of the function. It gives the entire signature of the function, which is actually not bad, in a sense that I like this signature. This could be the syntax for our query language. Look at this. Look at this mother flipper. Look at it. So essentially, maybe if you want to query, you do the following thing: return type, parentheses, and argument 1, argument 2, argument 3. For example, if I want to try to find something like color alpha or similar, what I do is I say, okay, I know it returns color, accepts color, and accepts float. That is a very cool way of describing that. So the cool thing about Coogle is that it's so easy to describe the signature of the function, right? It is so easy to just describe that integer to string, and there you go, or maybe string to integer or something like that, right? And it just like gives you something. So we need some sort of like a similar syntax for C functions, and I think this is perfect. I think this is perfect, actually. Right, so yeah, and you can probably also do things like const char or whatever, right? And it also should match. And these things should also match things without the star, right? So, but it should rank it a little bit lower. So can we make some parameters like star? It will search for any type in this exact place. Yeah, that would be nice, though we can't really use star because it's also part of the C syntax. We can maybe use something like underscore. That doesn't sound really that bad. Or maybe we can also introduce a parameter, something like integer, right? And essentially it will match a whole class of integers like int, long, unsigned int, and so on and so forth, and maybe like a real, which will match float and double, and so on and so forth, right? So you can have like a whole classes of types, right? And here this is any. Maybe also like any or something like that. So, but that will require like, you know, more development that we can afford to do today, right? So it's like outside of the scope of what I plan to do for today specifically, right? So it's kind of difficult to implement everything at once within 2 hours. So. But we can start with specific types, right? So I just want to be able to say, okay, so find me that, and it should be able to find one of these things in here. So that would have been a poggers. That would have been poggers if at least we could get the return type. So the problem is that we can't even get a proper return type. So that's the real problem here. So that's the real problem. So as soon as we manage to do that, we're good, right? If we can't do that, well, that's too bad. We can dream about different features of the language as much as we want, but if we can't get the return type, it's all that is pointless. So let's go ahead and just try to find a way to get the return type. So type spelling, so return pretty print, type def declaration and the line type. Is that something like a return? Well, I mean, return type, ret type. So maybe we need to take a look at the bindings generator. So return, like, the thing that upsets me about Clang is that the things that you wanna get, they don't have obvious names. They literally don't have obvious names. You wanna get a return type of a function declaration. It is not called a return type. No, fuck you, it is not going to be called a return type. You want to get the name of the function. Fuck you, it's not name, it's spelling. It's fucking spelling. You're gonna go mad, you're gonna cry, piss your pants maybe shit, the usual things, but it's not gonna be called the way you expect it to be called, because fuck you. Wait. I need a return type of the function declaration. It's not a return type. No, it's something else. Go do recursive search or something. It's not gonna be called return type. It's so goddamn upsetting. It's just like, why? You're making it more difficult than it should have been. Why? Why are you like that? Why? Anyway, because I'm asking for a very simple thing, right? I'm asking for a very simple thing. No, I'm not gonna give you that. So get type declaration. Okay. So this one is interesting. Get type declaration. But it's not. Return the cursor for the declaration of the given type. Oh, well, it's only needed when you already have the type. Alright, when you already have the type. Though, can we get the type of the cursor? We get the type spelling. Okay, so we get the cursor type. Okay. I think I know what we need to do. We get the cursor type, so that's cool. That is already very cool. Right, so expected some parentheses. I can't see Scheiße in this mist. Okay, so we don't really copy anything. I just want to get this thing. Okay, so it's a function proto, right? It's a function proto. So that means there should be some things for CX types to extract the different parts of the stuff, right? So this one is a CX type, and we can get the type spelling, but this is not particularly useful. So can we have a CX type? Type spelling, equal types, you can compare, get canonical types, is const qualified, is volatile. Okay, so we're getting somewhere. Get address space, get type def name, unified, unqualified type. Return, this is the type declaration. Ooh, retrieve the calling, it's a calling. Wait, is that what? Wait a fucking second. Retrieve the return type associated with. Of course, yeah, it's a result type, you dummy dumb. You thought it's a return type. Oh, you are C programmer and you were always returning your types from the functions. That's too bad because it's called the result type. Fuck you. It's not return type. You dummy dumb. It's a result type. I'm so sorry. It's just like I don't know why this makes me so mad. It's just like, and it's such a simple thing. It's such a little small thing, and it makes you waste a little bit of time, right? It's a small thing that wastes just a little bit of your time, but there's thousands of them. Like, there's thousands of them, right? But all of them are small, and all of them waste a little bit of your time, so you cannot blame a very specific thing. No. It's gonna be thousands of these things, like a death by 1,000 cuts. Like, I swear to God, those people. And those motherfuckers call it a return type in here, and then call it result type. Just to piss you off even more. They fucking know how it's supposed to be properly called. They know that this is how you're supposed to call it, but they call it result type because fuck you. Ooh. I'm sorry. Anyway, maybe there is a return type. Some people say get a return. No, there's no. Okay, so we can get cursor type, and then we can say, okay, get a result type, but that's not enough. We need to get the type spelling. Clang get type spelling, and then I can say copy and dispose. Copy and dispose. Alright. Yo, look at that. Fucking int, mate. Fucking int. So, what if it was void? Just like the one I have in my soul right now, after working with the Clang API, it is in fact void. Absolutely marvelous, meine Freunde. Absolutely marvelous. So the scheisse we can do now, we can say func return this, and we've got the return type. We've got the return type. So, and here, so I made a wrong assumption. So the only thing we care about is actually param declaration. Right, so we're taking all the children and we only taking the param decals and we add only them there. So that should be more than enough to basically get everything correctly. So here is the new definition of this particular function. So file name is that, row is 7, column is this, offset nobody gives a fuck. Arguments we have shader const char, and return is void, and this is because I specifically say that it's going to be void, but then we can do an integer, and that should update that as well. Yeah, so I suppose to do it like that one more time. One more time. I wonder if we can do query replace this, new line, maybe even this. One more time. This with new line. Boom. Look at that. Arguments is that. Return type is that. One of the things we can do, we can actually print them in their supposed the supposed form in that querying language that we come up with. Right, so that's one of the things we can do essentially. So let me try to do that. So I'm going to comment out all of that stuff. In fact, we don't really need any of these things anymore, so I was just like looking at them, we didn't need them. So we iterate into the functions, and essentially we can first print their location. So first comes the file name, right? First comes the file name, then comes the row, then comes the column, right? And then what we have a return type, and we're supposed to have the arguments. So arguments has to be like a separate thing that is built from the string builder, right? So we can provide the return, and here comes the args. So we need to take a look at how you use string builder. Yeah, there we go. So here's the string builder. So let's create a string builder in here. So let's call it args or something. And so builder, you basically appending things into the builder. To be able to append things into the builder, what you have to do. So let's first append the parentheses, right? And then we're gonna have this kind of thing. So after that, we need to start going through the arguments of the function. We're going through the arguments of the function. And if the index of the argument is greater than 0, so if it's not the first argument, we have to append a separation between the arguments. So we have to do append. Right, let's put then so we can see, you know, clearly where is the condition and where is the branch. So we're gonna add args, and I suppose all of that has to be pointers, by the way. That's very important, but I mean the compiler is going to tell me. I'm going to put like a separation like this in here. There we go. And then we are supposed to append the it, like so. So that constructs the basically builder, but then you have to materialize your builder with, I think, builder to string. Yeah, you have to call this function because builder is not storing its chunks in a continuous memory, so you have to basically bring them together into a single thing afterwards, right? So you have to do something like builder to string, and that will kind of create what you expect, right? So this is how you do like a string concatenation in Jai in sort of like a C style. So let's go to the compilation errors. So mismatched level of indirections. Oh yeah, this one is interesting. You're supposed to actually pass it in here by a pointer because builder to string modifies the internal builder. I think it resets it to 0 so we can use it on the next iteration or something like that. So somebody asked an interesting thing. It is shadowed. I hope so. Right. I don't remember if it is actually shadowed, but I'm writing this code with the hope that it does. If it doesn't, it's going to be sad, but I'm pretty sure it does, so it should be fine. I mean, you can always do something like arg, like this. It's just like, it's default. You can always change the name to whatever you want. It doesn't really matter. Okay, would you look at that? So that's pretty cool. Why do I have like a double of these things? Oh yeah, because I don't need these things. Why am I so stupid? There we go. So that's what we have in here. That's very poggers. I absolutely love that. So it would be kind of cool to also have a name in here somewhere. Let's actually put the name in here and also put like double colon. And here we're gonna have it name. Right, so, and there we go. So that's a very cool syntax. Imagine if C literally had this kind of syntax for the functions. That would have been funny, I think. Alright, but yeah, there we go. So here's the function, and here it's like, this is how you're supposed to spell it if you want to query it's like by signature and whatnot. That's how you're supposed to spell it. I think it's a reasonable syntax for querying the signatures of the functions and stuff like that. What do you guys think? And by the way, to answer the question, is it shadowed? The answer is yes, 100%, right? It is shadowed. Right, so we know that for a fact. So let's go to test.h and let's actually test that on a bottle source code, right? On the bottle source code, because that's the real source code we want to actually parse. Unexpected child kind type ref. Okay, so basically for the type ref, we're gonna say ignore. Right, sometimes we get those, and we don't care about them. All right, so that's what we get. Look at that. Okay, get mesh. That is absolutely perfect. That is just beautiful. Look at that shit. That simple, and we got all of them. We literally got all of them. So the question remains, how the fuck do we, like having something like this, how can we compare it to whatever the user is provided? Right, so for instance, this is like actual signature, and then we have a user input. And the problem with that is that the user input doesn't have to be super strict, right? What if the user like puts space in here? Like we should kind of ignore it, right? But what if the user like didn't put space in here, and that is also a reasonable thing? We have to somehow normalize these things, somehow normalize. Oh, right, that's right, tokenization. Okay, I suppose like the next step would be normalization, right? Basically bringing them to a singular form where this kind of stuff does not matter, right? This kind of spaces or the amount of spaces or the lack of spaces does not matter. One way you do that is you tokenize this thing, and you reconcatenate the tokens again with the same style of spacing. You know what I mean? Right. So essentially we can just tokenize both the signature and the input and concatenate them with a single space between each and individual token in here. Right. And then compare them. We can even compare them character by character. Right. Character by character. And here comes the punchline. Since they are normalized and we're comparing them character by character, we can do a freaking Levenshtein distance on them and rank them by Levenshtein distance. Huh? And that's how we can achieve this fuzziness. Do you guys know what is a Levenshtein distance? Like, do you know what is a Levenshtein distance? It is freaking awesome. Levenshtein distance. I'm pretty sure I didn't spell it correctly, but who cares? It's going to correct me anyway. This is a function, right? It's a string metric for measuring the difference between two sequences. Informally, the Levenshtein distance between two words is the minimum number of single character edits, insertions, deletions, and substitutions required to change one word into the other. So we can take the signature of the function, the user input, normalize both of them, and basically do Levenshtein distance between them and rank them by Levenshtein distance. The Levenshtein distance of 0 is going to be exact match. For example, if there is like one maybe argument missing, it's going to be some sort of like Levenshtein distance, some sort of like amount of modifications to that specific string. So it's going to be ranked a little bit lower. And so on and so forth, right? So it's pretty straightforward. And it is pretty straightforward. So I'm going to give the link to Levenshtein distance, and I'm also going to put the link in the description for anyone who's interested. And furthermore, we already looked into the Levenshtein distance on our channel. We had whole series where we implemented Levenshtein distance algorithm in Python, and also use that algorithm to implement diff utility in Python as well. Right. So all of that is going to be in the description for people watching on YouTube, and on Twitch I'm going to copy paste it in here. So there was 2 episodes where first we looked into the string diff in Python, and then based on that we implement file diff in Python, and we come up with a simple sort of like a project which is like diff in Python pif, and maybe I'm going to just steal some code from there. Right. So that was fun actually. That was actually super fun. Right. So, and having that code is going to be very useful because I literally forgot everything I was explaining in this series. Well, I kind of remember how to recreate Levenshtein distance algorithm. To be fair, I don't really have to remember. Like, you can take this function definition, right? It's a basically recursive function. Right, it's a basically recursive function, and then you apply dynamic programming in it, right? So you just like basically do memorization and you get like an efficient implementation on Levenshtein distance. So yeah, so stealing code from Toding, yeah. So stealing code from Toding. So that's basically my idea. That's basically my idea. I'm not sure if it's going to work out, but I have an intuition, some sort of like a feeling that it's kind of going to work, right? It makes sense. It does in fact make sense. So the problem is, how are we going to tokenize it? Are we going to like implement the tokenizer again from scratch? How many tokenizers I implement on the stream? Way too many, to be fair, right? But we can just use the tokenizer that is implemented by Nothings, right? So the creator of STB libraries, right? So we already look into that. Yeah, so we can just use this STBC Lexa, and we can even use bindings generator to create bindings for Jai. So since it's in C, it's super easy to use that in Jai. So we can just use this Lexa and just do that. Maybe there is a way to Lex this kind of thing using Clang. But I mean, I just don't want to use libclang, to be fair. Like every time I have to ask libclang to do anything, I just like, I want to cry. Like seriously, I really want to cry. And maybe piss my pants, maybe shed and come. It's just like I don't want to use Clang. This API is literally designed by trolls. It's just like freaking, they know it's called return. I will not forgive them ever calling return type result type. I will not forgive them that. It's just like, why? Like, you won't do that unless you want to troll people. It's like, unless you want to troll, you won't do that. But they did. Anyway, so I think I'm gonna use this thing. We're gonna do all of that, but I think, do you see this shit? Like, I can't continue like that. I can't continue, right? So we have a lot of, still have a lot of things to do. We need to integrate with Alexa. Then we need to implement normalization. And after we implemented normalization, we need to do Levenshtein Distance. That's like 3 things. And doing that without T, that's like, it's impossible. It's just like, how am I supposed to do that? This is like, we have to make a small break. We have to make a small break, but it's gonna be a quick one. It's gonna be a quick one, just 5 minutes. I'm gonna just brew some tea and I'm gonna be back. Don't go anywhere. All right, so let's go ahead and download the Alexa and see how we can even integrate with that Alexa. So I probably need to actually add it to the description in here, right? So we actually have to put it like that and download that. Row, there we go. We're gonna download it to row. I wonder if I can like literally use the bindings generator, the same bindings generator that we use to like parse this stuff. I think it should be possible, right? But that means we'll have to introduce like additional build step and everything. So let's download it real quick. So here is the STB Alexa. So the thing about STB style libraries is that they act both as essentially C files and headers. So, which means that you can precompile this thing. You can precompile a header-only library, essentially. So, as far as I know, what we have to do clang and just do -c stbc header. And I think we have to like explicitly use -xc so it doesn't try to do precompiled headers, but just treat it as the C source code. And we also have to add the the macro that enables the implementations of all of these functions, right? STBC Alexa implementation. That's kind of important. STBC Alexa implementation. Right, and I think that will literally compile that into the object file. We can even take a look at the names of this entire thing, and here they are. So essentially we can basically link with that object file, and if we have the correct definitions for all of these functions and also the definitions for the structures, it will basically work. So that's essentially the idea of the header-only libraries, is that by default they act like headers, but as soon as you enable this specific macro, they start to act like C files as well. So you have a lot of control over like where you put implementations of the functions and stuff like that. So that means we should be able to precompile it somehow. So if we take a look at the binding stuff, right? So if we take a look at the binding stuff, right, bindings generator. So there is example, but in example we have both CPP and H. And the way we compile them is rather interesting, right? So we just provide CPP, and that makes like a lot of sense, right? So that makes a lot of sense. We just like compile it like so. But does it really have to be like a dynamic library? So here they're suggesting to use it as a dynamic library, but I feel like using it as a dynamic library is kind of dumb. And the code that is generated for all of that, like for Linux for instance, is something like this, right? So they're using structures and whatnot. So maybe there is already STB. So the cool thing is that the standard library of Jai already contains a lot of STB things, and they are kind of precompiled. Yeah, they are kind of precompiled. Like for instance here, you just have these things, and I feel like they're manually generated. All of these things are manually generated, right? And for Linux, for instance, yeah, you have both .a and .so. Alright, so it is considered normal to keep STB libraries in DLLs in Jai and just link with them dynamically, but I mean, maybe here is for static things, here is for dynamic things. I don't know. I don't really know. So let me see what we can do. Okay, I'm gonna just like assume that maybe we do want to actually link all of that dynamically. Link as you wish, but I mean, how do I do that? Like, I don't know. What I'm doing here, I'm just following an example. I'm following an example in here. So here is an example. And an example, they use specifically dynamic library. Can I use static one? I don't know. The example doesn't tell me. Example specifically says dynamic. Does it mean that I cannot do static? Maybe I can just try to replace it with static. Will it work still? So that's the thing, is that it's just like doesn't demonstrate you. It demonstrates specifically dynamic. I don't know what that means. Alright, so let's actually remove this dynamic thing and let's do Clang, not Clang, but Jai, Linux, Jai. Is it going to work? At least it didn't crash, right? So it crashes with errors and stuff like that. So undefined symbol operator delete. So yeah, it doesn't know how to deal with this kind of stuff. But if we replace static with a dynamic, right, and we just do it like that, it seems to, it still doesn't work. Wait. Huh. Alright, so that means this entire thing is broken somehow? Is that what's going on? Wait, why this thing stops to work? Excuse me. Like, we checked it yesterday. It seemed to work. Did I somehow break it already? Okay, it's fine. Maybe some sort of a stuff happened in here. So let me see. Like, what is going on? All right, so you cannot do static. You cannot do static because you have this like undefined symbol. You have to do dynamic. I don't know. Maybe I'm doing something wrong. I'm just like, you know, following the instruction, trying things out, and I can't do that. Sorry. So that means like the only thing you can do here is the dynamic thing. So it is what it is, and it isn't what it isn't. Interestingly, maybe we can just do the manual thing, but the problem with the manual thing is that I have to manually come up with the declaration of the structure and stuff like that, and it's kind of like a pain in the ass. I don't really want to do that. Right, so STB, Lexa. So, and for the Lexa, so this is basically the definition of the Lexa. Like, I don't want to do that. I really don't want to do that. Looks like I have to. So here it is relatively straightforward, right? So you just do Alexa init. You just allocate the structure for this entire thing. And then you just do the input string store. Oh, string store is actually rather interesting. So it's storage with Alexa that can use for storing past strings and identifiers. And this is the storage length. So this is pretty straightforward. Right, so there we go. Okay, so let's introduce the build script. So we're gonna have first Jai, which is the build script. Right, the way you write the build script, you have like a run section, and then let's take a look at some of the examples, right? So you're supposed to actually do that by an example. The bad part of the build scripts in Jai is that they're kind of difficult to come up off the top of the head. Like, I can never remember like what kind of function they have to call there, so they're not particularly intuitive. I'm sorry. Sorry to tell you that. Yeah. So obviously the first thing you have to do, you have to set build options DC do output false. Obviously, in a build script, that's obviously the thing that you have to do. Very intuitive, right? So like, I'm sorry, I'm too dumb to actually comprehend this as an intuitive thing to do. I do understand what it does, right? I do understand what it does. Essentially, when you call a compiler on first.jai, it means that you're supposed to compile this thing. It's supposed to have an output. To turn it into a compilation script, you have to say during the compilation, oh, we're not producing the output, so please, during compilation, DC, during compilation, don't do output. So let's try to compile this entire thing. So we have a build CPP static, disclaimer, language isn't finished. Yeah, this language isn't finished. Try doing the same with CMake. Yeah, I know. I know. That's why I'm saying that I'm just dumb. I don't know what I'm talking about. I'm ignorant, dumb, arrogant. That's it. So, so I need to find the build CPP script thingy, right? Because I just want to have a similar function. Really? I can't. Wait a second. Are you telling me that it's not even available there? It is something internal. Where am I supposed to find it then? Why couldn't I find that? Am I an idiot? Am I an idiot? Right, so, right, I'm an idiot. Because, well, okay. But where is the definition of this thing? Where is the definition of this thing? Where is it? Am I just like, what? Oh, oof. Okay. Oh, and you have extra spaces in here. Oh, I see. You just have extra spaces in here. You're supposed to do build CPP. Okay, the reason why I care about this stuff is because how do I enable, how is it called, the macros, right? Do I enable them outside, right? Do I enable them outside? So enum CPP, free CPP. Okay, so I suppose I have to sort of like pre-process this entire thing a little bit so I can use it. I think this is something that they do as well in STB. I think that's one of the things that is happening in there. Well, there's no even the headers. So if I take a look at printf, yeah, so it doesn't have all these things. Okay. Build CPP, build CPP. Okay. STB Lexa. Okay, so I suppose the easiest way to do all of that is STB C Lexa. Lexa implementation, and just to rename it to C, right? Is that what you want to me? Like, I mean, it's not difficult for me to do a very dumb solution. It's not very difficult. I'm just not sure. Is that how I'm supposed to do that? Really? If I want to interface with this STB C Lexa, literally, that's what I have to do? Like, I'm just not sure. That's what stops me. It's not like I don't know how to do that. It's just like, what's the right thing in Jai? Really? Like that? Is that what I'm supposed to do? Or is there something better? Or no? I can continue, right? So I can continue doing like a horrible shit. Okay, so I'm gonna continue doing horrible shit because something better is not obvious for me. So don't blame me. I'm just stupid, ignorant, arrogant, and stuff like that. I just wanted things to work. I just want things to work. Okay, so let me see. So we need to have like a first.jai and right, so I'm not like I'm stalling, not because I don't know what to do. I'm just like, really? Like, is that what I have to do? It's a little bit yikes. It's just, but I mean, if this is what I have to do, sure. Like, I mean, I don't mind. It's just like, are you guys okay with that? I'm okay with that. So we're gonna do it like that. Build CPP static. So this is gonna be STB C. So was that? STB C Lexa, right? So this is going to be STB C Lexa, and we're going to put STB C Lexa C, right? So that's one of the things we can do. In fact, we can do something interesting. we can only try to build this thing like that, right? So we're not trying to build everything yet, right? We're only trying to build the C code, right? So then I'm going to do jai link first.jai, and it fails because we need to import the compiler, right? So we imported the compiler. So what else do we need to have in here? So it's a build CPP. Build CPP, right? What do we have? There we go. So we're building this scheiße. Look at that. Look at that beautiful dot A. Beautiful dot A. Yo. So, and this is how we got it. This is how we got it. So by default it uses GCC. It's kind of cool that it automatically detected that this is C. It's not using G++. But I think if you do GCC on CPP, it also will automatically do that. So. Alrighty. Now we need to have maybe like a STB module of some sort. Maybe STB module or maybe something else. I'm not quite sure. Let's create stbc lexa.jai. So, and I'm gonna just steal a little bit of a code from Jai. So this is module stb images, and let's take a look. So there's some declarations in here, and depending on the platform, we're including different things. So let me see. Oh yeah, I see. stb image. We can say that we have stbc lexa, and the library is just stb C lexa. So this is how we declare an external library, so to speak. So this is an external library. So now we probably need to define the structure. So where is the structure for the lexa? So here is the lexa. Here's the lexa. So how can we convert that to Jai? We can call it stb lexa, like so. And I suppose we just have to go through all of these things and change them like so, right? So this is the character. Is character a thing in Jai? I think it's U8. Yeah. It's called U8. So we have to do this kind of thing like so, and then boom, pointer to U8. Int, in case of an integer, as far as I know, it is 32-bit integer. So you have to do int 30. What is the 32-bit integer in Jai called, chat? I forgot. S32. Thank you so much, Sushi. Thank you. Really appreciate that. Right. So who needs Chat GPT when you have the real chat? You know what I mean? Alright, so we can remove that. This is U8 and then U8. Long. Is long 64? I forgot. By the way, why do we have music in here? Like, why nobody told me that we're listening to music? Alright, so main.c. What's the size of long on x86-64? I think it is 8. I think, maybe not. Size of long. Clang, main.c, main. 8! Okay, so let's just use integer then. Because if I remember correctly, by the way, this has to be not double colon, I'm an idiot. Could we replace space double colon, just that. Oh, it's fine, whatever. So double, does Jai have double or float 6? Okay, float 64, that's fine. This is integer, and this is U8. String 2. String 2. Okay, so S32. Can I say, bruh, this is C structure. Like, basically padded like a C structure. Is there any way to say that? Do I have to, like, I don't know. Chat, do you know? Does anybody remember how to do that? Like, because in any, like in all of these languages, there's some way to say, okay, like it's just like pack, C or whatever. There's a way to disambiguate. Okay, so the Jai uses the same way of padding the structures as the as C, right? So they're packed the same way. Okay, thank you so much. All right, I believe you, Sushi. That is Apogers, my friend. That is Apogers. All right, so let's just find the function initializer. So this is what we need. Not what we deserve, but that's definitely what we need. So this is the function. Here we accept the pointer to stb lexa, right? Then we accept the pointer to u8, and this is basically the end of the string, right? So this is the end of the string. Then string store, right? This one is super important. And integer strong length s32. So this is one of the important functions that we'll need. So we also need a way to get the token. Okay, so let's just bring that stuff in here as well. I remember that you have to do something like equal stb c library. I don't quite remember. So maybe stb image, stb printf. How do you do that? Yeah, so you have to do foreign, and you say it like that. Okay, that's cool. Yeah, foreign stbc lexa. Okay, so we need that, which is going to return s32, and it's accepting the stb lexa like so, and it is in fact foreign as well, stbc, my god, lexa. Cool. I think that's everything we need in here, right? Do we need anything else? I don't think so. stbc lexa. So maybe we'll need get location, but not for now. We'll need some of the enumerations, that's for sure, but we can just basically copy paste them at some point, so that's totally fine. Okay, that is very Apogers, woggers. So let's remove that. So this is main, this is not what we need to remove. That's pretty cool. Okay, so let's do first, it still compiles. We need to continue the compilation essentially, right? So we managed to compile that, but on top of that we need to compile the rest of the things. So this is examples. So we generated bindings, we didn't really need to do that. Let's create the workspace. We are creating an executable with the name, I think it's currently called main, so that's totally fine. And then we don't really need interception, I think. Right, we don't really need interception, so that should be fine. So that's literally it, right? So that's literally it. So let's call it Coogle. Though we can make an executable literally called Coogle. I think it's a little bit better. I think it's a little bit better. So we have to add the file. I forgot about that, right? So add build file. Add build file. So that should be fine. So maybe somewhere here. Options. We have to first take those options from somewhere. Where do we get the options though? Yeah, so we have to grab them from here. That's very important. Go, and it compiled. Beautiful. So in the main thing, we probably need to load the stb c linker Jai. Let's try to literally load it. So I put everything in here, right? So I suppose that's fine. Okay, so it's semicolon. I have to put semicolon in here. Unable to parse. Oh yeah, you're supposed to put arrows in here. Sure. Okay, what else do I want from me? Okay, loaded library, shared object. Do you do static library? How do you do static libraries? I know that there is a system library. Is there something like static library? How can I do that statically? We need to find an example. we need to find an example on how to do that. So is there something like static? Library, no, of course. The language isn't finished. 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 Okay, I'm sorry. Okay, Coogle. Okay, so everything seems to be compiling. We can take a look at the final thing in here. Does it contain Lexa? Well, it doesn't. Yeah, probably it got nuked by the optimizer or something like that. But anyway, so let's go and maybe disable all of this stuff in here and try to play with the Lexa. Right, so let's try to play with the Lexa. That was hard, but we managed to do that. We managed to do that anyway. Right. So let's allocate Lexa on the stack. STB Lexa. There we go. It is on the stack. So, and let's call C Lexa initialize. So we provide a pointer to the Lexa, and we need to have some sort of an input stream. So let's actually create maybe some sort of a query. So when the query is going to be, we want to find a function which returns the caller, but accepts another caller, right, another caller and the float. So how are we going to do that? We have to provide the query at the beginning of the stream. I know that this is a data, but instead of the length, we have to provide the end of the string. So we only have the length of the data, but we can do something like query data plus query count. And I think that's how we get the end. So we also have to provide the string store, but this, if I remember correctly, I already used this library. This is needed if you're gonna work with string literals, right? And I think they even say that explicitly. Right, so string store is a storage lexicon used for storing parsed strings, and it... Okay, you need a little bit of a memory there, right? You need a little bit of a memory. So we can pre-allocate that. We can pre-allocate a little bit of the memory. String storage, we can do it length. So let's say that we want to have maybe 1 kilobyte. So I think 1 kilobyte is going to be enough for everybody. And we're going to do string storage. And I think it's just like new U8, like so, right? So we're allocating this amount of stuff, and then we can just like literally use that string storage. Right, string storage len. Len, like so. And one of the things we can also do is, I suppose we can even defer freeing that string storage at the end, if you feel like it. Right, if you're coming from the C++ environment and you're a little bit scared of this kind of stuff, so this is what you can do. Okay, so we can try to print the content of the Lexa and see if it actually got initialized or something. And let's just go ahead and do that. Let's just go ahead and do that. So we're going to try to compile this entire stuff. It doesn't compile. So declaration of the argument requires two-value bake. So it wants... Okay, so let's find the definition of the new function. Obviously, it's not the way I think it's supposed to be used. So it's something like... Maybe it's a new array. Actually, I think I kind of remember... okay, so it's not the way I think it's supposed to be used. Of course, I can always find the definition myself, sure. So it's something like new. Let me find it. All right, show me how you're supposed to use this. Right, so we provide the type. Okay, so I think it's kind of like a new array. Yeah, it's new. First comes the count and then comes the type, and it's a new array. Okay, sure. This is how we're supposed to use that. So string storage len, yeah, sure. Whatever. Just let's get this over with. All right. So there's no. Okay, I don't care. Whatever. Let's not free it. Let's leak the memory. So mismatching types. So you want. So it gave you the array. All right. That's actually pretty cool. So it literally gives you the array. So that means you need to do the data. And then the string storage count, which means that it doesn't really matter if you have the separate variable for that. So we can just do it like that. There we go. Okay, so that's way better, I think, maybe, almost. Loss of information. Wanted S32 but got S64. I mean, that's totally fine. Just cast it. Just XX. Just cast it there. What else do we have in here? Success, whatever. So what do we have? Let's try to run this entire thing. So Coogle. Alright, so did we get... Okay, so we got some pointers in here to the beginning and to the end. And it does in fact look reasonable, right? So this is the begin and this is the end. Parse pointer, string storage. So string storage is 1 kilobyte. Okay, so that's totally fine. And string 2, all right. Everything seems to be fine. Everything seems to be fine. So we're good. We're Gucci. We are Tamaguchi. So let's see how you're supposed to use this specific lexer, right? So you're supposed to like keep using tokens. Okay, this function returns non-zero if token is parsed, or 0 if at the end of file. And then you're supposed to get the token IDs out of the lexer token, right? Makes sense to me. So returns non-zero if token is parsed. While stbc get token, we provide the lexer, and this is where we're supposed to get the tokens, right? So token is supposed to point at token ID, right? We can try to even print those tokens ID. So how many tokens we're supposed to have here? 1, 2, 3, 4, 5, 6. We're supposed to have 6 tokens. We can just literally print the token IDs and see if there is a 6 token IDs after we did all of that. All right, so we're gonna do Coogle. It still didn't compile because I forgot semicolon, and let me see. We've got some IDs. There are 6 of them. There is 6 of them. So we managed to actually tokenize this entire shit. To be fair, I spent so much freaking time trying to interface with this lexer. I could have actually written it from scratch. Enjoy. Right. So anyway, all right, so we now need to be fair, I don't care about the token IDs. So that's the thing. I really don't care about the token IDs. What I do care about is, okay, this one's interesting. Null terminated string for collects qt string as qt identifier. Yeah, I'm interested about the text. I'm only interested about the text. So real number is a double constant value for Well, we can actually kind of limit what kind of tokens we even gonna get there. So collects float. So let me find the definition of this. Where is it defined? Okay, it's enumeration. All right, all right. It's enumeration. It is in fact enumeration. It's supposed to be like a token in the lexer. So lexer token variables. So what I'm thinking is that maybe I can move this entire thing here. I can move this entire thing here, but that requires giving them a name. What is a collects? C lexer. Can I call it collects? Right? Is that a good name? I don't freaking know. Query replace collects underscore with nothing. And I remember there was a way for enumeration to actually say the type of the enumeration. Right. So token. It's supposed to be integer, right? So are they integers by default? Is that how we're supposed to do that? I don't remember. Right, so I know that the Jai is able to do that. So enums, yeah, without this thing, right? So there we go. Maybe we can even say S64. All right, and the token here is collects. So that way, we can actually print their names and know precisely the types of the tokens. So if I try to build this entire thing, semicolon, oh yeah, it wants the semicolons instead of the commas. So let's quickly query replace all of that stuff. Hopefully that will work. I don't know if it will. Semicolon. Oh, it wants semicolon here as well. Loose data assignment are currently supported at global scope. Eh? Do you want me to do something like this? Is that what you want? Alright. Enum out of range. Okay, so what the fuck do you want from me? So it wants enumeration. Yeah. So maybe I should have actually read. Yeah, so I suppose... why is that out of range exactly? Why it didn't work? I have no idea, honestly. Honestly, no idea. So there's something weird with this Lexa and why it's... so if it's 256, I suppose this one is going to be 257, right? So, and so on and so forth, right? So that's what it's supposed to be. Oh, wait a second. So if they're out of the... okay, so this is obviously an ID. And then 40 means it's an open parent. Okay, so I see what is going on in here. I see. I think I understand. Right. If Lexa token less than end of file, you have to treat it as a character. Can I turn this into a character? Treat it as a string. Is that something I can do, chat? Right, because, okay, I can do a string, which is just something like this, so then I can do... I can just allocate this stuff as 0 Lexa token, and then just print. This is a dumb way of doing that, chat. This is a dumb way of doing that, but I think it may work. It didn't work because you can't modify it like that. You can have a character, I suppose, right? So you can just have a character and you can reassign the token to the character. I mean, U8. Then you can construct a string, which is data appointed to this and a count equal to 1. And then just print that. Yeah. Now, that should be enough, maybe? So do I expect anything else except things that are less than end of file and IDs? I don't think so. I do not really expect anything else. And if it is an ID, I need to be able to know like where it is located, what is its name. Like I want the actual sort of string and whatnot. Next, right, get token. So null terminated string for, yeah, it's identifier, but there is no such thing as Klex identifier. All right, so that means the string is probably what I need. All right, that's cool. So if it's an ID, if Lexa, so we don't have to do that, Lexa token ID, right, so, and we can just do string 2, of course, and toString. Right, there we go. Otherwise, we can do something like unsupported token type, this thing, and this is going to be Lexa token, and let's see what's gonna happen. Look at that, minor Freunde, look at that. Do you see that Scheiße? Do you see that Scheiße, meine Freunde? Do you see that? That is absolutely epic. We can use that to normalize. How are we gonna fucking normalize? We're gonna create a string builder, right? So we're gonna have a builder and we're gonna have a string builder. And essentially, as we iterate those mother flippers, we're going to be appending them. We're going to be appending them to the builder. So let me show you how we're going to be doing all of that. All right, so this is going to be append builder pointer to that, and like literally just s, just add the s. And in here also append just this. Just append this. But on top of that, we can append like this additional space at the end of them, right? So additional space at the end of them, and then we can materialize the normalized token. So we're gonna put it in here. I'm gonna actually put bars in here so we know precisely like what extra spaces we have in there, and we can do builder to string, and then we provide the builder. Emacs, don't be a dummy dum. Okay, here is normalized signature. So essentially, when we have some sort of a signature, this is how we can do that, right? So this is how we can normalize that. And so this is needed to actually precisely compare them together, right? It's needed to precisely compare them together. All right, so that's pretty cool. Maybe we can turn that into some sort of a function, if you know what I mean, some sort of a function. So essentially, we're gonna normalize like a query or whatnot, right? So normalize query, right? So, and the query is going to be just string, and we're going to return another string. So this is how it's going to go. And we're going to accept, we're going to basically copy paste everything in there and return builder to string. Return builder to string. So essentially, it's not a bad thing that we're gonna have this extra space, right? So if all the normalized signatures are going to have this extra space at the end, that's gonna be totally fine, right? That's gonna be totally fine. So the only thing I care about here as well is how do we clean up the memory afterwards, right? So here we allocated some shit. So there's basics. How do I free? Is there something like free? Free. Okay, so you can provide the memory. Is that everything I can free? I can just provide the memory. Is there free array? New array. I need some examples. More examples would have been nice. Memory management free. Okay, so okay, you allocate array, but you free the data. I see. So this is how you're supposed to do that. Okay. So we can defer free string storage data. All right, that's cool. So I suppose we don't really have to free anything in here because STB selector doesn't do any memory management, right? So that's why it requires you to allocate some stuff for the storage data. So that's totally fine. And for the string builder, I think we have to actually deallocate the string builder. String builder. Free buffers. Free buffers will be deprecated pretty soon, and only entry point to resetting is going to be a reset. So builder to string. I know that builders to string already kind of deallocates a little bit of a stuff. How do I dispose the string builder? Does anybody remember? Right, I don't quite remember, because I remember there was some way. So there's the free buffers, but it's not really resetting. So there is a oh, okay, so this one is good. When builder to string, it defaults to do reset. Yeah, builder to string do reset, and do reset could free buffers in line with the bucket, and reset freeze the buffers and reset. Okay, so as soon as you did builder to string, there's nothing to worry about. So there's no memory leak in here anywhere, right? So, but yeah, the only thing we have to worry about is then freeing the memory allocated for this string. Okay, so that's kind of important. So essentially, normalized query, normalize, that's a very unfortunate name. So normalize query, we can do color float, right? So we can print normalized query, and we should not forget to then free. That's basically roughly what we have to do, right? So maybe even defer it like that. So there we go. So in terms of memory management, we're good in here. I think we're good in here. So that's pretty cool. That is pretty cool. Okay. But that is not particularly enough, I think. Right, so we have a function, right? We have a function. And now having a function, we need to construct a normalized query. So we need some sort of a function here. Function as normalized query. So here we're going to accept f, which is going to be a pointer to function 2. Function 2. Maybe we're going to even do using. And in here, we're going to return this string. Right, we're going to return the string. And so let's create the builder, string builder. So append builder return. Can you provide like also space in here? Yeah, there we go. Then maybe I can even provide something like this. Yeah. Then I do args append builder return. Actually, if it index greater than 0, then append this thing. Right, append this thing. I'm just not sure how to better deal with that. Right, so then we need to do append builder. This is not enough. Man, this is not enough. Because you may have several tokens within a single argument. You may have several tokens within a single argument. This is literally not enough. Okay, so we need to split it in two. The first thing just creates the signature as it should go, and we already kind of have that. Right, so we already kind of have that in here, but not fully. Right, so not fully. So let's do something like function query. Let's call it signature. But let's not be confusing. Using f function 2, and it should return string. So string. So we'll still need a string builder, right? We still need a string builder. So, but here we're gonna append builder name. So not the name return, but maybe then this thing. Then for args, if it index is greater than 0, then we append space to the builder as well, right, to the builder. And if not really, just like append builder it, and that's it, right? And then just at the end append that and return builder to string builder. So function signature. So this is the first thing we have to do, and then we'll have to normalize that. So that's how we're gonna go, right? Because a single argument here may contain several tokens, and normalization may require like just do another path in here. All right, so function signature and stuff like that. Now, what I want to do, I want to try to just see how the normalized stuff is going to look. So build args or whatever. Function signature, right? So this is a function signature. I provide it, action provided by a pointer. In fact, I can iterate array by a pointer. In Java, you can put a star in here and you iterating it by a pointer. So this is going to be a pointer automatically. Right, so this is a signature. And then we can do normalized signature. Normalized signature. Right, normalize query. And this is going to be signature like that. And then we're going to print specifically normalized signature, right? Specifically normalized signature. There we go. So we might as well maybe clean all of that afterwards, but it doesn't really matter, to be fair. So it doesn't really work as easily as I thought. Procedure. Okay, so you cannot do several of these things, unfortunately. Okay, so let's just do it like that then. And of course, you have to do it like that. Alright, so we've got all of these things, and as you can see, all of them are normalized. All of the signatures are normalized. There's a single space between each individual signature. So now, what we can try to do, we can try to organize the process of searching. Right, we can organize the process of searching. For instance, I want to have a query, right? So I want to find all of the functions that have color, right? Return color, accept color, and also do the float, something like this. How can I find them? The first thing I will probably have to do, I have to normalize the query. Normalize. I don't really like this name. stbc lexer normalize. Right, so something like this. I think it's a little bit better. So normalized query, stbc lexer normalize. We provide the query, and we have now normalized query. As we iterate all of these signatures, all of the functions, right, we're normalizing them. stbc lexer normalize. And if, for now, we're not going to do a fuzzy search. We're not going to do fuzzy search. We're going to like compare them exactly. We can compare them exactly. If normalized query is exactly equal to normalized signature, we're going to print it. We're probably going to print just signature. We don't really have to normalize it. So here we have a query, and here is the code that performs the search. Right? It filters out all of these things. And as you can see, apparently I didn't know that, but there is also fade that also accepts color and float. We already freaking have Coogle. It's just without the fuzzy search. The only thing we now need to do is add a fuzzy search. Right. And how can we do that? We can do Levenshtein distance on normalized query and normalized signature. And we don't really have to filter, we have to sort in the ascending order by the Levenshtein distance. That's what we have to do. Seriously. So that's literally it. And that way we'll actually find more things, right? So maybe we can have like an upper limit. So we ignore everything that has like bigger Levenshtein distance than 100. Right, so that's gonna be kind of cool. We can try to search for other things. Right, can I search for a thing that returns color but accepts 3 floats? Is there something like that? I'm pretty sure there's nothing like that, so maybe it should accept actually 4 floats. Look at that. There is such thing. It's a color from HSV. Right. So that's cool. That's actually cool. That's already useful. That is really fucking useful already. Okay, so but if it accepts 4 floats, there is no such thing, unfortunately. Yeah, there is no such thing. Is there something that, for example, we can say void accepts 2 integers and also a string. So this should be init window. Yeah, init window actually found it. Easy. And as you can see, you can provide like any amount of spaces in here, like you can be like very imprecise, it will still match it, right? So because we tokenize and we normalize everything correctly. So, look at that Scheiße, meine Freunde, look at that Scheiße. We got some subs. I think, no, we don't get subs. Nobody pays any money to me. we got some subs. All right, so yeah, literally the only thing that is left is the Levenshtein distance, and we can just implement it on two strings, right? So essentially Levenshtein, maybe just lev, and in here is going to be like A accepts a string, B accepts a string, right? And then just returns an integer. So the thing about Levenshtein distance is that you need to build a table to actually properly do that. Right, so we can go into the details of how exactly it works, but I don't think it is, we have enough time for all of that. We don't have enough time, but maybe we do. Maybe we do. So essentially, Levenshtein function accepts one string and a second one, and answer the questions how many edits you need to make to A to get to B. How many edits you need to make? That's a very interesting question. So you can think of it as a function of two pointers, right? So essentially, on top of accepting strings, it also accepts the indices within the strings, right? So it accepts A, like I, let's call them I, right? So I is an index within the string, integer, and J an integer. And essentially, we can have something like, my favorite example is basically, you have add. How can you turn add into daddy, right? So it's like, you just have to add D and Y in here. So the Levenshtein distance between add and daddy is 2, right? So it's a very convenient string. So this is A, and this is B. So, and essentially, right, I is going to point at here, right? So this is that, and J is going to point at here somewhere. So, and what the function actually answers is basically, so I acts like sort of like a slice, right? So it acts like a slice. So we're answering that question for this entire string. So it is very useful because then I can basically go back on one and answer that question for that string, right? So it basically acts like a slice, right? So it's essentially slice. Maybe we can even call it a length. So in that case, it's going to be pointing at here, right? At full thing, but yeah. So we're going to consider them maybe lengths, right? And if we're going to consider them lengths, we're going to have n and m, right? So I think it makes a little bit more sense that, right? So essentially, here is the storage for the data, and here are the slices, and we can just move them around and stuff like that. So that's actually pretty cool. That is actually pretty cool. And essentially, we can ask several subqueries, right? So we can ask several subqueries. We can do lev a b n minus 1, right? A minus 1, but m, a minus 1 by m, then n but m minus 1, and then both minus 1, n minus 1, and m minus 1, right? So we can try to answer that. So if you do n minus 1, right? If you do n minus 1, essentially you're asking, how do I turn this string into this one, right? How do I turn this string into this one? What that means, what that effectively means is that you're asking how to turn this string into that one, ignoring this character, and then if you add one, essentially you're answering the question how many edits you have to make if you just decide to remove this character. So these answer the questions about removing the character, right? So this corresponds to the action of removing this thing, right? So that's basically how it goes. So the other one is gonna look like this, right? So how many edits we have to make to turn this string into this one, right? And then essentially we answer the question how many edits we have to move if we decide to add this character in here. So this one is going to be +1. And if we remove both of them and ask this question for these two substrings, we're asking like how many edits we're going to take if we decide to replace D with Y. right? As you can see, we just do three different actions, right? We do remove, add, and replace. And our goal is to find the minimum amount of edits we have to make to get from A to B. So what that means is that we just have to take a minimum between all of these three situations. I'm not sure if I explained it really well, right? So a better explanation is available on my YouTube channel, right? So like there's a whole series about diff in Python. I think I explained this kind of stuff better in there. I'm gonna put it like in the chat for people in here, and for YouTube people it's going to be in the description. So since both like all of the three branches here +1, we can just do +1 like this, right? So as you can see, each individual sort of recursive call corresponds to one of the actions. This is adding the character, removing, and replacing. And we just go through all of these situations, and we're just trying to find the minimum. And yeah, so the minimum is going to be the answer. So there should be some sort of a base for this recursion, and the base for this recursion is when one of them becomes basically 0, right? So essentially, when you're trying to say, like, how many edits you need to make to turn completely empty string into that one, well, you need to add this amount of characters, which means that if n is equal to 0, right, is equal to 0, then the amount of m, and if m is equal to 0, then the amount of is n, essentially. Right. So that's basically the base of the recursion. That's basically the base of the recursion. But the problem with this kind of approach is that, and by the way, we literally got this, right? We literally got this. We forgot a very interesting situation in here. Essentially, we need to take a look at the last character, right? So we know that there are some characters in here, right? Because if there's no character in first string and in second string, we basically return out of recursion. So if the last characters of these two strings are equal to each other, there is literally no reason to replace them. They just stay as they are, right? And in that specific case, we just like ignore them. Like we just ignore them. We return Levenshtein AB n-1 m-1, like so. But otherwise, we return the minimum out of those three. So that's basically the entirety of the Levenshtein algorithm, right? And as you can see, like we basically repeated this entire thing. But they're doing that from like a different end, right? So as you can see, they're doing that from a different end. They're also using like a tail function. But what we did in here, we just like used like an additional thing in here. It doesn't freaking matter. Right. But the problem with this thing is that it's exponential. It is an exponential thing. So you need to use dynamic programming to actually turn it into at least square one. Right, so essentially you may notice that what you're doing in here with n and m, you're effectively iterating a two-dimensional table, right? You're iterating two-dimensional table. So you can basically allocate that table, right? You can basically allocate that table. And I suppose the table is going to be like the length of both of these things, right? So I wonder if I can allocate a two-dimensional array. So new array. I can only allocate a one-dimensional array in here, right? So, oh boy. Yeah, so we can do something like new array, and we can go a count +1, right? A count +1 multiplied by b count +1. In fact, we probably want to maybe assign n to a count and m to b count, right? So we have the sizes as these values, and we don't really need to pass that stuff anymore. It doesn't really matter. So this is going to be dp. This is going to be dp, and here we're just allocating n+1 and m+1, right? n+1 and m+1, like so. And this is going to be an integer, right? So I'm going to comment it out because it doesn't really correspond to the reality anymore. It doesn't really matter. So Yes. And we need to essentially start iterating on those, right? So we can start with I, which is going to be from 0 to n, right? So including, right? So that's kind of important. And for j, 0m, also including. And we can kind of translate this entire thing. We can kind of translate this entire thing. So I suppose, like, if you look at this table like so, right, so let's say you have these kind of things. I'm an idiot. There we go. So this is the table. All right. So we need to initialize the edges with in increasing values, right? So 1, 2, 3, 4, and so on and so forth. And 1, 2, 3, 4, and so on and so forth. So the edges is going to be like that, right? So I suppose we can do it like this. I 0 n. So, and let's say this is going to be the row. So this is going to be dp row multiplied by column m plus 1, right, plus 0, right. So we're iterating the rows, so that means we have to just do I, and then we're going to do j, which is going to be m, and this one is going to be just the first one, j. We might as well actually print that entire table afterwards, right? So we can print that entire table just to see if it's actually doing anything. Let's go ahead and do that. So I'm going to be iterating through all of this stuff one more time. So it's going to be j and m, and let's literally print them. So it's going to be like this, space dp I multiplied by columns plus j, and this one is going to be a new line. Right, so I'm going to disable all of the code in here, and I'm going to find the Levenshtein distance between add and daddy. I'm going to see what is going on there. Okay, so it doesn't compile, semicolons, who cares? There we go. So we literally initialize this table like that, right? So at the edges we have this kind of stuff, so everything is fine. Everything is fine. So afterwards, let's do the iteration, but starting from 1. Right, so we're going to do the iteration, but starting from 1. So, and this is basically what we have to do in here, right? So we have to do these things. So let's see. If I equal to j, and I suppose we have to do -1, right? Because they can be equal to n, so that means they're gonna overflow. We have to use dp from the previous one. We have to use dp from the previous one, so we have to replace this thing with dp. Right, so I -1 multiplied by m plus 1 plus j -1. It would be nice if we just had two-dimensional arrays. But we just don't. Well, I mean, we wouldn't have to return this kind of stuff. So essentially, we just have to do it like that. So the current value has to be equal to the previous one. Yeah, that's basically what we have to do. Otherwise, the else situation is basically the minimum between those three. The minimum between those three. But also +1. The minimum between those three. So let me see. So it has to be. I might as well copy paste this kind of stuff. Alright, so this is going to be the first one. Then we have to do the second one, and then we have to do the third one. So this is -1. This is -1. This is that one, and then both of them. Yeah, there we go. So theoretically that should be it, right? And this is basically the entire table. The answer to the Levenshtein distance is in here, and it's 2. So the Levenshtein distance between add and daddy is actually 2, because you just need to add 2 characters in here. And that is correct, right? So like this is the answer in here. So basically here's the, like the table of different situations. We pre-computed all of the different situations, and yeah, we know the answer. We can return that answer like at the end of this function. We can just literally return dp, the last one. We can do something like count -1, because it's going to be at the end anyway. Right, and that's basically it. Again, I explained this entire algorithm in details in those series in Python and stuff like that. Right, so I just like replicated this algorithm. We can try to print this entire thing, so that should be fine. Right. And one of the things I forgot to do is that I probably need to defer freeing this entire stuff, right? So this is going to be dp data free this entire stuff. Okay, so this is the Levenshtein and everything. Cool. Now we're good to go. Can we actually sort the functions by normalized query? That's a very good question, actually. So probably, but it would be nice to maybe pre-normalize the signature. You know what I mean? Right, because we can just basically do qsort. Where is the sorting algorithm? Is there a module sort? Oh, I don't remember. Where is the sorting? Sort. What was that? Okay, quick sort. It was a quick sort. Alright, right. Where is the definition of quick? Okay, it's in the sort. So I can just use this thing. But that means that on each comparison, I'll have to do normalization. You know what I mean? Like on each comparison, doing normalization is kind of like a too much, in my opinion. So I didn't think it's a good idea. We can maybe cache the normalized signature of the function somewhere here. Normalized signature, like so. And we can even pre-compute that normalized signature while we're collecting everything. Actually, we can do that. I think that makes sense. That makes a lot of sense. So this is the normalized signature. Yeah. So let's actually quickly do that. Like right before we add to the final thing in here. So this is the function. Defer free signature data. Right. So we won't need that afterwards. After we did that, and then we can just do func normalized signature, right? So yeah, that's actually perfect. Like that's a perfect place to add that there. So now we can just do func normalized signature, so we don't have to do that all the time. Right. Okay, so let's go ahead and just do the sort. Let's go ahead and do the sort. So we're gonna provide the functions array. So this is the functions array, and we have to provide the function that accepts 2 functions, right? So the function 1 and function 2, a and b. So what's going to be the result? The result is supposed to be like an integer. We can make it an integer, right? So quicksort helper. So f, yeah, so it compares it to 0, so that should be fine. And essentially, what we want to do, we want to find 2 Levenshtein distances. Lev from query to a normalized signature. Actually, we have to do normalized query. Normalized query. And LB, B normalized signature. And essentially what we're comparing now is their Levenshtein distances to the query that we have in there. That's what we're doing. So how are we going to be doing all that? Like, I don't remember. So if we're doing this thing is considered less, so that means we're subtracting LB minus LA. I think that's what we want to do in here. I think that is basically it. I think. So now we can take maybe first 10 of the functions, right? First 10 functions. Maybe we can even do like a minimum between 10 and functions count. Right, and probably have to do -1. Afterwards, we can just go ahead and print them. So this is going to be print, but we need to print their locations, otherwise it doesn't make much sense. So this is going to be the name, and this is going to be the signature. Right, so it's going to be functions it. I want to actually use f. Right, so this is going to be f file name. This is file name, f row, f column, then f name and f normalized signature. All right, I think we're good to go. So let me try to compile all of that. It doesn't compile, let's go through the compilation errors. So what does it say? This look, oh, because I put the war separator. What else do you want from me? Semicolon. What else? All right, so that's fine. So function signature undeclared. So it's not it, it's func. Right. So it's the func that we're okay. So that should be fine. And this is a quick sort because we have to do the sort in here. Attempt to do variance, normalized query. John left us with blue balls. Like, like what? Is there any easy way to solve that? Context time. Okay, so that's actually a pretty good idea. Context time. We can put that into the context, sure. So yeah, let's just do it like that. My God. Add context. Normalized query. Why would you leave us with blue balls? Like, why? It's just like we're almost there, and it's just like the last thing just fucked us over. So okay, it's fine. Yeah. What else we have in here? Is not a member of. Oh, it's a function too. Yeah. Okay. Are you guys ready? Okay, that was weird. I forgot to put new line in here. So what we're looking for? We're looking for... Okay, so let's actually first search specifically for caller, which accepts caller, and float. Something like this, right? So we're looking for these things. Let's do the usual bit, and what do we have in here? Okay, I feel like it sorted them in not correct order, right? This is not a particularly correct way of sorting them, so let's actually swap them. Look at that. Holy shit, this is so fun. Sound. Yo, it fucking works. Right, it found a similar function, like for sound. Levenshtein Distance is all you need. Literally, Levenshtein Distance is all you need to like, have this smart thing. This is so fucking cool. Holy shit. Alright, so I don't know. So like if I wanna find a function that regulates the volume, right? It accepts the sound and accepts the float. Can I find something like that? Can I find something like that? Set sound pan sound. It finds this kind of shit and it's all, oh my god, this is so fucking cool. It actually finds them. Like I can put the signatures and it freaking works. So the thing that maybe accepts vector to and accepts to float. Do we have any function like that? Okay, so set mouse scale kind of work, but there's no thing that actually returns a vector. Right, the closest thing we can do a void. This is so freaking cool. Right, so because we're normalizing everything, it just works. It just works exactly as you want it to work. That is so fucking cool. Holy shit. And what's interesting is that you can have typos in your thing. Right, I'm not even freaking joking. You can do like a caller, and because it's a Levenshtein distance, it's still going to work. It autocorrects the typos. Who did they just came up with a god strategy? It's so cool that you like, yeah, it is so robust. It's really robust, like because Levenshtein distance is literally all you need. It will just autocorrect everything. Holy fuck. So, I don't freaking know. Like, we can try to find some other functions that maybe accept two integers and maybe const char star and maybe return caller, but it does not necessarily have to return caller, right? So it has to return something else. It may return something else. It will still find something that is very close. The closest thing is probably initialize window, right? So int const char. So what if we had something like float integer? So what's the closest thing would be? Still init window. Right, what if anything like this? So measure. That's so cool. Measure text. So we just invented Coogle. It's sort of a prototype, right? Because we have a lot of things hard-coded, but this is sort of like a, yeah, it's literally a prototype. We can maybe rewrite that in maybe a different language, right? So the language that everyone has a compiler for. The problem with Java is that not everyone has a compiler for Java. Maybe turn it into some sort of like a website as well. Right, this is extremely freaking useful. Holy shit. This is extremely freaking useful. I think I should continue working on that, right? So because, yeah, it is as useful as Coogle, as the original Coogle. So maybe we need to I don't know. I want to commit that and basically upload to GitHub. But I don't know, this is very hacky. It's not really reproducible on anyone's machine. That's for sure. It would be better to maybe rewrite in C and just like document how you link with libclang. So this is certainly like an internal prototype, but I'm surprised that it freaking works. I'm surprised that it freaking works. So yeah. And we implemented all of that stuff in 2 streams, right? So we started with not even knowing how to parse C. Like I literally started yesterday's stream, like I don't know, do we have anything to parse C? I didn't expect that we're gonna get to this stage where we have actually something that could compete with Coogle in terms of like fuzziness and usefulness and stuff like that. Right, that's so awesome. Fuck. Cool. And we didn't even implement things that allow you to put like underscores in here, right? Or maybe, to be fair, Levenshtein distance is already like fuzzy enough. Honestly, it's already fuzzy enough. I'm not even sure if I need to add any more like smart syntax or anything like that. It's already kind of okay. It's already kind of okay. All right, so I guess that's it for today. Thanks everyone who's watching right now. I really appreciate that. I'm gonna think about how we're gonna go forward with this project, right? Because again, this is just a prototype. I just tried out the idea and the idea seems to be promising. I'll think about how we're gonna continue that. Maybe we're gonna do more streams on that. Thanks everyone for watching, and I see you all on the next recreational programming session with Azuzin. I love you.